The general uniaxial medium represents a thin sheet of a uniaxial material. As a complement to the ASAP realistic retarder model, it's useful for describing devices specified by their physical thickness rather than optical thickness. It can exhibit reflectance, and the details of how that is specified also distinguish it from the realistic retarder model. In this example, we have a general uniaxial material quarter wave plate with the reflected modes set up so that we not only transmit circular polarization from a linear input, but we also reflect respective S and P polarization states in this test case. Let's take a look at that in the 3D viewer. So in the 3D viewer, the upper case is S polarization. The lower case is P polarization, as they're labeled. If we take a look at the upper case, we see that the polarization coming in is transverse to our viewing, so that is S polarization. And the reflected mode is also S. The transmitted mode is circular polarization because the general uniaxial model is rotated 45 degrees relative to this plane of incidence. One application of the general uniaxial model is in C plates. These are thick plates of uniaxial material with the crystal medium aligned along the direction of the optical axis of the system. I'll show two examples of this. One C plate, the one on the left, is perfect. The 90 degrees here denotes that it's been rotated so that its polar angle is coincident with the system axis. Compare that to the one on the right, where we are approximately 90 degrees, but we assume that layers of this material have walked off of the optical axis slightly. This could happen in all kinds of material processing and is a typical problem we might want to solve to investigate the effect of a defect. So first let's run the undistorted form and see the result. What we see is a system with polarization interference as we go away from the system axis. The center is the system axis, and as we walk away from it, we're going out towards 90 degrees from the system axis. So you see a classic Maltese cross with polarization interference between the center and the edges. So we see several bright rings with the Maltese cross sort of T-shape superimposed on it. If we compare this to the distorted form, we see that we no longer have fourfold symmetry in the system. And in fact, there are 4 orders or 4 bright rings in the 2 quadrants to the left and only 3 bright rings on the 2 quadrants to the right. Moreover, there's a little bridging between the second order on the left side and the first order on the right side. If we were using this as a compensating layer in a liquid crystal device, this would mean that our viewing angle characteristics would be different on the left side of the screen than on the right, which is not usually a good thing. To demonstrate a system-level application of the general uniaxial medium, this is a simple Lyot filter design. Lyot filter is a classic design that obtains extremely narrow spectral transmittance peaks. It uses multiple retarders with a harmonic thickness relationship to obtain very narrow lines with large free spectral range between the lines. In this case, we're designing a filter with a center wavelength of 590 nanometers, and we're going to do a spectral scan to look at how it performs from 450 to 775 nanometers. Just to show you the basic characteristics of the design, we have 4 linear polarizers rotated 45 degrees. These are this stack of rotated squares with 3 general uniaxial material layers between them which are retarders with thicknesses in the ratio of 1 to 2 to 4. Just to peel this apart a little bit, I'll hide the first polarizer, and you see the first wave plate. Then the second polarizer, the second wave plate, the third polarizer, the third wave plate, and the fourth polarizer, and finally the detector. So, just to remind you, the wave plates have thicknesses in the ratio of 1 to 2 to 4. The first one has a retardance that is 5 waves retardance, the second one 10, and the third one 20. And this harmonic series is what comprises a Lyot filter. So we see here a plot of the spectral performance of this Lyot filter design on axis, its normalized transmittance both in theory and using the ASAP General Uniaxial Material model. If we want to examine how closely theory and ASAP come to each other, one way we may do that is by looking at the narrowest peak. And you'll note at the narrowest peak that we still don't see a gap between the two. So let's expand this until we fill the screen with it. And now we see small gaps. Let's take a look at the spectral band that we are considering as we look at these gaps. At the low end, we're at about 491.4 nanometers. At the high end, we're at about 491.9 nanometers. So this is about a half nanometer band that we're considering here. So we'd consider these gaps to be relatively small. That was intuitive from the original view, but it's always good to scrutinize the details. Another place where we might expect some deviation is at the baseline, but even there, we see very, very small gaps. Just in case you might be skeptical that the narrowest line is the best place to look, since the higher lines are lower order peaks, let's take a look at one of the higher wavelength peaks. And if we expand this, we still don't see significant gaps. We're at about 736.8 here, about 738.1 here, so this is about a nanometer and a half, but this was a broader peak. But we're really having a tough time peeling these two characteristics apart. So my conclusion is that on axis, the Lyot filter performance model using ASAP agrees very well with theoretical values.